It's going to be a squeeze to get everything in an hour, but we'll see what we can do. And I'll keep going. And if anybody wants to come back for the recording, that's fine also. The outline, I'm going to, let's go back. Yeah. I'm going to recap a bit of Haskell just so the relevant bits are top of our minds. Do that really quickly if I can. And then look at a couple of examples of monads, which I'll describe. I won't tell you what a monad is just yet, but we'll come to that. IO and maybe. And then we'll look at a first pass of monads in the fourth section. And then we'll go through a kind of traditional way of building up to monads, functors, applicative functors, and then monads, which is what some of the people have done from time to time. And that's quite helpful. But I think getting the big picture first helps you to kind of see where you're going with that route. And then actually look a little bit at the history and look at what's beyond monads if we get a chance. But do interrupt me with questions, because questions are going to be really valuable, I think. And particularly if you don't understand something that I've said, let's try and clarify it together. Everybody okay with that? Yeah, good. Okay, so quick whistle-stop tour of some of the bits of Haskell. It's got various built-in types: string, integer, and bool. I think you've all been swatting up Haskell, but I'll just go through this quickly. So you can define a value using a literal, like a string. And you can also define list values using expressions with square brackets. And Haskell infers the types, so you don't need to declare the types for those kinds of definitions. Right, functions take a single value and produce a result. So classic example is lowercase, which lowercase is a string. And so we could read that code out as lowercase as type of a function from string to string. So the arrow is the function symbol. And crucially, functions are applied without parentheses usually. So f of x, f space x is a way of writing the function f applied to x rather than f brackets x. If you get functions with more than one argument, they're carried. So each argument is applied in turn. So if you get a remainder function, remint, that takes two integers, it actually takes a single integer and produces a function from integer to integer. So that remint signature there, int to int, is really int to a function from int to int. Okay, that's just an example of where Haskell's functions start to kick in. And when you apply that, you apply remint to 3 and 2. You'd expect to get the answer 1, I think. But remint of 3 is what's applied first. And that gives you a function, which is then applied to 2, which gives you the answer. And then we get into generics, or polymorphic types, as they're called in Haskell. So it's easy to see this with an example. If you take a head function, head of a list, it takes a list of any type and gives you an item of that type. It can actually fail as well, but that's not in the signature. Lowercase variables are used, lowercase names are used for polymorphic types. And the compiler will fill in the concrete type that when head is used in a program. You can also have constraints that limit the types that a polymorphic type covers. So take the sign function. You can't apply sign to any old type, unlike head of a list. So you can constrain the type A here to be floating. And we'll come onto what kind of thing floating is. It's actually a class. But it's saying that A has got the right methods, right operation on it, if you like, to do floating point operations. And if that's the case, then sign is defined and it maps a floating point to a floating point value. Lambda notation is probably familiar from other languages, but the spelling is a bit different in Haskell. It uses a backslash instead of a lambda. So backslash s, x arrow, x times x is a lambda expression, which takes an x and produces x squared. So it's an anonymous function. And again, Haskell will infer the type, and it sees multiplication there, so it says A has got to be a number, numeric type. Then we've got higher order functions. We've already seen a higher order function actually, because the remainder function took a value and produced a function. So, but you can also have functions that take a function as an argument. And we've got one here, map, for example. So map takes a function from A to B, from type A to type B, and then it takes a list of A's and it gives you a list of B's. So it's applying a function to all the values in a list and giving you the list of results. And just an example of that, if you now the times 3 in a brackets is an abbreviated way of just applying the multiplication function to a value 3 and leaving you with a function like a triple function. So that brackets star 3 is like triple as a function, which just is a mapping from a number to a number. So mapping that across the list 1, 2, 3 just applies a function to each of the values 3, 6, 9. Okay, just talk about defining classes, sometimes called type classes. That gives you a way of overloading functions and using them with multiple types. The class is a declaration of the overloaded operations, class methods, if you like. So an example is equality. Class equality on a type A has 2 operations, equals and not equals, and they're in brackets because they're infix operations. So when you wrap them in brackets, they become prefix operations, normal functions. And they're used for comparing 2 values of type A and giving you a Boolean. And there's a default implementation of not equals here. Not equals is defined in terms of equality and the not, logical not. Yeah. Okay, so when you've got a class definition, you can then declare instances. Say that a type has an instance of a class, and then you actually define the overloaded operations. So suppose you've got a type shape, and I haven't been through data declarations, but that's basically an example there. So there are different alternatives for the shape data type. It's either a square which takes a float, or it's a rectangle which takes 2 floats. So if you like, it's a square with a length of a side, or it's a rectangle with the width and the height. And if you want to make shape an instance of equal, then you just have to overload the equality operator. And you can do that like this in stages. This is got the equality operator here, and this expression is saying this square of x is equal to the square of y in the case where x, well, if and only if x equals y. So it's taking this expression with equals, and it's pattern matching really. It's taking the shape and saying if the shape is a square of something, and it's being compared to square of something else, then those 2 shapes are equal if x equals y. And then we fill out the other examples, so other cases. I'm not going to spend a lot of time on this. And you make sure that it's symmetric by defining r equals s in terms of s equals r. And you get not equals for free in the type definition. Okay, so, but we don't need to get into detail. We won't see much detail in the rest of the talk, but the thing to remember is that there are types and instances, and we'll see that monad is a type. Right, type constructors are worth knowing about. It's a function that takes a type and produces another type. And we've already seen one, square brackets. That takes any type you like, any concrete type, and produces a list of that type. So list of string, square bracket string is a list of string. It's taking one type, string, and producing another type. So that's a whistle-stop tour. I hope that was all reasonably familiar. Probably won't need it all in the rest of the talk, but it just sort of get the juices flowing, as it were. So let's look at input-output, I/O. Now, the big selling point about Haskell is the functions are pure. There are no side effects. They call them effects in Haskell, no effects. But Haskell code can have effects. You've got to be able to do input and output and network traffic and this kind of thing. So it's a bit shocking when you first come across this apparent contradiction. They're both true, thanks to monads and thanks to some machinery in Haskell. So let's look at an example. What do you think happens in this case? GHCI is the REPL, the interpreter of for Haskell. And what we're doing here is taking a running get line and binding the result to str, then entering a string hello, and then running this putstrlen on str plus concatenation with exclamation mark. What do you think the output might be? Or is muted?
Well, we're all expecting hello exclamation mark, but actually I must admit I didn't realize that would work in the REPL outside of a do block.
Oh, right. Yeah. Essentially, it's like a big do block. We'll come on to do blocks later, but yeah. Hello exclamation mark. So essentially, you've got a program there that's done some input and then some output, and how can that possibly be? So, what are the type signatures of those functions? GetLine is it doesn't give you back a string; it gives you back an IO string, and we'll come on to what IO means in a little bit. But essentially, it's a string wrapped up in the IO monad. And putstrlen takes a string and gives you another IO value. This time, it doesn't really have a return value, so it's using the unit type, just parentheses. Unit type is like void in some other languages. Its only value is parentheses again. It's a single value in the unit type. So that's the type signatures. What's going on there? Okay, now these are called IO actions. So IOA for some type A is an IO action. And the way to think of it is it's a direction for doing IO, a command specifying IO to be done. But it's not doesn't actually take place until the IO action is run. And when it's run, an IO action is only run when it's bound to the main program of the main function in a Haskell program. So essentially there's one IO action, at most one, in a Haskell program, and when you run that, it then runs the directions incorporated inside it. So you can think of the program as it goes through the function calls as being building up a more complex IO action, and then when we run main, bang, the thing runs. Okay, so there are no side effects in the construction of the function, but there are side effects when you actually run the IO action. And in particular, there's no way to extract a value from IO. You can't get from IOA to A by any means. Once you're inside the IO monad, you stay there, and that's crucial to maintaining this kind of division between the effectful main and the pure functions that can create the IO actions that go together. So that's a first example of a monad. We haven't talked about the details at all, but it gives you an impression. And the concept is that a monad is a context for execution, and it kind of, in some senses, protects the rest of the program from that context. And you can put things into that context. Sometimes you can get them out. In terms of, in the example of IO, you can't get the value out. As Adrian spotted, that execution, that experiment, is equivalent to this do block. And we'll come on to the do syntax later. But essentially, it's just a single program, and it looks quite imperative. It looks like it's actually executing a get line. You could imagine a semicolon there, and then putting out the string. But it's actually, that's just syntactic sugar for something more complicated. It's a function. Main is a function, and it's comprising get line and then a lambda expression. And the two are put together with this bind operator, which we'll see is an operation of the monad class. Okay, so So we haven't got anything imperative here. We've just got a single function. Okay, so that was one little intro. Something that's a bit more tangible, a bit more easy to work with is a maybe monad. And maybe is just a data type that's defined, I shouldn't say just, maybe is a data type defined like this. So maybe of a type A is either just A or nothing. And you can think of it as a computation that can fail. So just X is a successful computation of the value with the value X, and nothing is failure. And of course, we'd be interested in diagnostics and that kind of thing. And there are other constructs in Haskell like the either monad that allow you to have a failure with diagnostics or something else. But it's the same principle as this, so we'll keep it simple for this talk. Monad maybe turns out to be a monad. So what are the functions that you need for a monad? Well, these are the specific ones for maybe. Return, oddly named return, which we'll come back to the naming maybe later. But returning essentially takes a value and puts it into the monad, puts it into the monad context. So return of X is just X. It wouldn't make sense for return of X to be nothing, because that would throw the value away. So here we're taking the value X and plopping into the maybe structure. And then this bind operator has got quite a complicated signature, which we'll delve into later. But it basically it's taking the first parameter is a value of the maybe A. And then there's a function that takes an A and produces a maybe B, and that produces a maybe B. So essentially what we're doing is we're taking a value in the context. We're kind of pulling the value out of the context under the covers and applying a function that produces another value in a context. And then we're giving back that value in the context. And the implementation of that is like this. So we've got a case statement, which we haven't actually covered, but it's pretty obvious. It's a pattern matching of X. So if X, this maybe A as input is nothing, then the output is nothing. We just don't apply the function at all. We skip it. If the maybe A is just Y, just a value, Y, then we apply the function F. So X bind F here. We apply F to Y and we get a maybe B. So the answer is either nothing or a maybe B. So it's a maybe B in type. So that's the first exposure to this bind operator. We'll come back to that in more detail, so don't worry if you haven't grasped it yet. But essentially, return adds something produces something in a monadic context, and bind allows you to operate on a monadic context.
There's something that was quite helpful for me on that last example. I think I mentioned it to you, Liam, was when I realised this is basically what safe navigation or the Elvis operator does in a bunch of other languages if you've used that. So you're navigating down some structure and you do question mark dot or whatever it is in your language of choice. And as soon as you hit a null, it propagates the null safely. Otherwise, you keep on navigating the path. That's exactly what this is doing.
Yeah. So error handling in Rust is similar with a question mark. Allows you to kind of ripple up errors to the containing function immediately without continuing. Same sort of idea. Okay, let's look at an example, and it's a bit busy, but it's actually fairly straightforward. Suppose you had a safe divide function at the top here, and it just takes two floating point numbers in carried form. And if you divide by 0, if y equals 0, then it returns nothing, else it gives you just the division. So the result is a maybe float. It might be a float or it might be nothing if there's been a divide by 0. And let's look at how that would get applied if you didn't know about monads. Let's define a calc function, and it's going to take this sum. It's going to calculate x divided by y plus y divided by z plus z divided by x. And if x, y, or z is 0, it's going to give us nothing. So that calc function takes three floats and produces and maybe float if there's been an overflow. And if you just do it in a very basic way, implement it in a very basic way, you have to kind of pick your way through this and say, if safe divide, let's divide x by y first. If safe divide blows up and we get nothing, then the result of calc is nothing. Otherwise, if safe divide gives just f1, then we can do the other divisions and carry on forward and end up with just f1 plus f2 plus f3. So that's x divided by y divided by z, and z divided by x. Okay, so essentially it's handling the error cases by hand, and this is the sort of thing we see in lots of languages, is exception handling or if then else is to cope with the failure cases. But if we go back to the do notation, so if you go back to the bind, we'll come on to do in a second. If we rewrite this using bind, which has got this automatic way of propagating errors, then it looks like this. So safe divide of x and y bound to this function. So we do safe divide of x and y first, and then bind the result into this function, this lambda expression. And of course, if safe divide xy is nothing, then bind will make sure that the result is nothing. We don't need to kind of explicitly worry about that error handling. And then we go through the same process with safe divide yz, safe divide zx. And if we come out at the end of that without nothing, then we end up with f1, f2, and f3 that need adding together. And then to keep it inside the maybe, in other words, to return a just value, use return. We could code just there, but since we're talking about the monad, we're using bind and return as the two monad operations. That's still pretty messy. It doesn't have any explicit error handling in, but it's still pretty messy. If we bring in the do notation, now I'll talk about the do notation again later to explain what it actually is, but that's like syntactic sugar for that that bind operation, a set of bind operations. And this looks really neat. So you can attach the results of safe divide to f1, f2, f3 and add them together and return the result. And the do notation just unpacks, it's desugars to the bind operator, and you get all the free error handling that we had previously. So that's a kind of advantage of using a monad for error handling. So with that in mind, there's two examples in mind. Let's have a look at monads in the general case. We've seen IO is a context for IO actions to encapsulate side effects, and maybe is a computation that can fail, encapsulating errors. And this is the definition of the monad class. So we can see that M is a type constructor. The monad M is a type constructor. So what that means is if T is a type, then so is M of T. So just think of that in terms of the monad, the maybe case. You can have a string type, and maybe string is the monad type for string, the maybe monad type. And then the signatures of return and bind look like this. So return takes any type and returns you the monad equivalent of that type. So it's that type in the monadic context, if you like. Where M's
just a historical question, Glenn. Do you know, I mean, you mentioned it before, like I would have called it lift. Do you know why they call it return? Is that because of like the IO monad use, or is it some other reason why it's return?
The only time I've heard return discussed is negatively.
Right, okay.
It's all hindsight. I've not actually seen the original rationale, because there are a couple of downsides of return. I mean, can you see what the downsides are?
Well, I don't know. It makes me think of returning a value, which is not really what it's doing at all. So
that's right. So returning a value, and usually in most programming languages, return interrupts the flow of control, doesn't it, and makes you exit the current function. Return does not do that.
No, it's lifting or wrapping or whatever you want to call it. Yeah.
Yeah. So when we come on to some of the other, when we come on to applicatives, we'll see the naming is a bit better there, but we've just got to live with it because this is the name.
Just is what it is at this point. Yeah,
it is what it is. And bind, similarly, it's got this double arrow equals, but it's pronounced bind, and we get used to that. But at least doesn't have any connotations from other languages to confuse us. So return lifts a value into a monadic context. Lift would have been a good name, wouldn't it? Like you say. Bind takes a value in a monadic context, and a function that takes a value and returns its result, puts its result into a monadic context. And then bind takes that function and essentially applies it to the value. Not quite that, we'll come on to the details later.
You use the word lift and think it's quite natural. I don't think it is that natural. I think of it pushing something down, not lifting something up.
Yeah, you can draw the diagrams both ways. I'll show you some diagrams later, but if you draw them a particular way up, it's lifting. If you draw them the other way, it's pushing down.
Okay, great, thanks.
The introductory texts don't really talk about this function in the middle. And for me, that's really crucial to see that, because it's a funny shape. It's not taking an A and mapping it to a B. It's not taking an MA and mapping it to an MB. It's lopsided. It's taking an A and mapping it to an MB. And that's called a Classley arrow type, for what it's worth. But it's just worth giving it a name, because we'll see that come up time and again. And it's that makes Monads special. We'll come back to that. So this is where we talk about the do notation in a bit more detail. So if you have a series of do's, a do with a series of sequences, here we've just got two operations, then it gets desugared into a series of bind operations. And if there are 3 items in the do, essentially the first rewrite first desugaring is to turn that into a do. And in this case, it will be S is bound to get line, S is assigned get line, and then do puts to in S, and then the remainder. So essentially you break down a multi-line do into 2-line do's. And then each 2-line do desugars to a bind operation with this lambda expression. So it's a really nice notation. It is a bit confusing because it makes people think they're writing imperative code, but that's, in some senses, it's quite comfortable when you first come to Haskell to be able to write something that looks imperative and get away with it. But we've always got to remember that it's not really imperative at all. It's just a way of writing a function. Okay, this is where we talk about lifting and the diagrams. So we've got our definition of the monad class there. And because of the way this is drawn, lifting makes sense. So we've got X of type A. We're going to use the return function, and we end up with return X, which is of type MA, where M's the monad. So it's lifting it into this monadic context. So the idea is we have the base values at the bottom of the diagram, and the monadic values, the monad context at the top of the diagram. And the bind operator is a bit trickier, but essentially it's hinging around here. We're binding y and f. So we're taking a value y and binding the function f to it. And suppose y is the value here, and it's of type MA. Then what we're essentially doing is we're pulling each of the x's out of y. So each value of type A, we're saying for all x in A, we're going to go down to the next level down, essentially, take out the value from the monad. We can't return that to the code. That's not possible. That's not a monad operation. But in terms of implementing the bind operation, it's as if we did extract a value out and then apply f to it and end up with f of x. And because there might be multiple x's in y, and we'll come on to that later, these somehow get merged together. So the context for y, so if you think in terms of I/O, the I/O context for y gets carried across into the I/O context for the result. And yeah. Does that make some sort of sense? It's not an easy one to explain.
I mean, I definitely get the two arrows. For each X in Y, I'm going to have to sort of hold on till we've seen some examples.
Yeah. Well, think of it initially in terms of the maybe monad. So if we're talking about nothing, if the value of Y is nothing, then there is no X in Y, and we're done. If it's just X, then we can take that X and go around the loop, apply F to it, and get the just F of X kind of thing, or F of X at the other side.
Have you got an easy example where there would be more than one X? That's the thing.
We'll come on to that.
Okay.
The list monad is when we'll come on to that.
Yes. All right.
Yeah. Monads have got to
how does the function, the Kleisli function, Kleisli arrow, how does it deal with multiple values? Because it's a function which takes a single value and produces a monadic object, which presumably has multiple values in it.
Ooh, that's interesting. Well, actually, no, it doesn't. It produces the Kleisli function here, F, takes a single A and produces a single MB. Okay.
Oh, yeah, I understand. But the MB has potentially multiple things in it of type B.
Right.
Just like the MA had multiple things in it of type A.
Yeah. If the particular monad allows many X's in Y, then there could be many X primes in B as well, right? So I guess that's how it's...
Yeah, I mean, the intuition is it's a bit like a kind of flat map operation. It will flatten the results. So the MBs get combined together with the context from Y to produce a result context. So you can see the values passing through this way, but the context can be massaged in essentially fairly arbitrary ways. And that's one of the complexities.
Depends on the bind operation, the way it's massaged.
Yeah.
Oh, I see. Okay.
Yeah.
Right. Yeah.
Okay. Now we've seen the operations on monads, but for a type to be a monad, the operations have got to obey some laws, and they look a bit fiddly at first, look a bit tricky. So we've got this 4 equal signs is kind of equality or equivalence. So if we take X and put it into the monadic context and bind that to F, it's the same as F of X. So going back to our diagram, if we pull the value out and return X, we get X, apply F to it, and then we're done. If you take a value and then bind the return operation to it, you just get the value. And there's a kind of associativity, but that's pretty unpleasant to read. So if instead of this bind operation, we write the laws differently, they look a lot cleaner. And you can compose Kleisli arrows using this operator, the less than equals less than. And it's just like function composition, but for these Kleisli arrows. So essentially you take an A mapped to MB, B mapped to MC, and you get an A mapped to MC. And the order is a bit like function composition. It's the wrong way around, if you like. But if you rewrite the monad laws using that Kleisli arrow rather than bind, then they look a lot simpler. So it's saying return composed with F is F, F composed with return is F, and F, G, and H composed together can be done in any order. It's associative. So I think the laws make a lot more sense if you look at it in those terms. But that's there in the original. It's just harder to read. Okay, so if you ever implement a monad, it's up to you to kind of check that these laws apply. It turns out, ordinary programmers hardly ever have to implement a monad because the monads are implemented and ready for use. So that's kind of like a whistle-stop tour and a high-level view of monads. To give a bit more insight, I now want to build up to monads in stages. And the way you do that is we talk about a thing called functors, and then applicative functors and monads. And these are similar structures, similar operations, similar types, if you like, but get progressively more complicated. functors now. So this you can sort of take you can breathe a sigh of relief now and look at something that's really concrete. We've talked about mapping across lists already. So we had that map of the triple function to 1, 2, 3 gives us 3, 6, 9. Okay, that's mapping. And the type signature of a map is it takes a function from A to B and then maps a list of A to a list of B by applying the function to each item in the list. Okay, that's straightforward. So a functor is any type constructor that can be mapped over. So it's not restricting it to lists, it's generalizing it. So you could think of a tree, for example. If you had a tree of a particular type, then you could apply a function to all the nodes in the tree and end up with a tree of mapped values. So what's the class definition look like for a functor? Looks like this. Now, unfortunately, because of the way namespaces operate in Haskell, they couldn't use the name map again because of the conflict with the map for list. So they called it fmap, functor map. And fmap takes an A to B function like we had before, and then it takes f of A and maps it to f of B. And so f is a type constructor. So in the list case, f was the square brackets. In maybe, f will be maybe, and so forth. It's basically allowing any type constructor to be declared to be a functor. So some examples of that are list, we've already seen. IO turns out to be a functor, and maybe. So yeah, you can probably guess this, but in the definition of the list functor is that fmap is equal to map. Okay, that's just good news. Ordinary list mapping to do fmap, and so we can rewrite the example and say fmap of triple 1, 2, 3 is 3, 6, 9. Okay, so that's very straightforward for lists. It's very familiar. IO's a little bit different. So we have to define fmap for IO. We say that IO is a functor, instance functor of IO. And so the functor implements the IO type, if you like. And fmap of f of x just takes x and binds it to return composed with f. Now that's a bit mind-blowing, and it's also quite tricky because bind and return are monad operations. And why are we using monad operations to define a functor? Because we haven't even got to monads yet. It turns out that IO is kind of built into Haskell, and so the bind and return operations are built-ins, and so we can use them to get the right effect here. But essentially what it's doing is saying if we have an IO, say IO string, for example, and then we wanted to map a string to something else, get an IO of something else, we could use fmap to do that. So let's look at a concrete example. If we take, if we fmap this hello plus plus, which is a function, it's a bit like triple the way it's defined. So it's partially applying the plus plus, the concatenation infix operator. So that concatenates hello on the front of a string. And if we fmap that onto getLine, then we get an IO action. So x here, if we look at the type of x, GHCR lets you explore the types, :t. Then x is of type IO string, and string is actually an array of characters, it turns out. I don't know why GHCR doesn't say IO string here, but it tends to expand down to the lowest version, but you can think of that as IO string. And then if you actually run x, this is like binding x to main, then it will prompt for a string. You can type in world, that will be the result of getLine, and then fmap is applied to that, and you get hello world. Okay, so we've applied a functor to an IO value. Is that reasonably clear?
Yeah, I'm just sort of like, I think of fmap as mapping over like a sequence of things, or a sequence, a set, a something, a structure. I wonder what the structure is here. Like if I had a do and I had 3 get lines, would it map over all of them?
Ah, right.
Obviously, it would from the definition. I don't know quite what would happen there.
No, I don't think it would, because it's taking the result of the function here. So
Yeah, so as it is, yeah.
an IO string. So if you had a sequence of get lines, and I don't know what you do with them, but massage them in some way, then the result would be some sort of IO string, and then fmap would apply to
And then
that.
it would just, yeah.
Yeah. This is a single function. There's no way that fmap can kind of look inside the definition of get line and pull it apart, because it's essentially already executed by the time it runs.
You're conflating two functors.
Okay.
The list functor and the IO functor. If you want to map that over all of the IO results in a sequence. Is that not right? You'd have to obey them all in sequence, put them in a list, and then map over the list.
Yes.
That makes sense to me, but I can't explain why.
Okay.
What, Chris, are you talking about what Steve just said, or this example?
Yes, Steve's explanation.
Okay. Yeah. Yeah, I mean, if you wanted to, I think what Steve was saying was, if you wanted to do a series of operations and map over them, it'd be up to you to capture that structure in a list.
Yeah, yeah. Clearly, we could do that. If we had a function that returns some kind of a list, then we could map over it.
Yeah. So you could imagine a do block producing an IO of list of string, and it could build that up by doing a series of get lines, and then fmap applied to that would first of all, it would map into the list of strings, into the IO, and then it would have to apply to the list of strings. So you might need two lots of fmap there. I'm not quite sure. Be a good example to try.
Yeah, I guess a clarifying way is that now my thoughts are a bit clearer. Fmap, I mean, so prime for mapping feels like one of those for each kind of example, for each x in this, do that. And I think what we're saying is, in the IO case, there's only ever one x in there.
Yeah.
That just felt a bit strange, but yeah, I get it.
Yeah. Okay. Functors have some laws. Not going to dwell on this, but they're pretty straightforward. So if you take the identity function ID and fmap that, you're going to not change the structure. So you not change the values. So it's the same as ID applied to the value. And taking a composition of two functions, G and H, is the same as mapping fmapping one and then fmapping the other, and composing the two together.
Can I ask where the 4 equal signs came from?
Oh, okay. Yeah, I think I got them from the Haskell wiki. Actually, they're not really part of the language. They're just a way of talking about the language.
Whereas equals
Like
equals is,
equivalent.
right? So that would be confusing.
Yeah.
Yeah. Okay.
That's right.
Right. Thanks.
Okay, so at last you can do some work. In my lectures, when I've kind of just to set the scene a bit, this is kind of a distillation of several lectures that I gave in the second year at Winchester University last semester, and I've kind of pulled out all the lead in and put it into one place. So the students would have been gradually introduced to some of these concepts over a period of weeks, rather than scaring them silly and giving them everything in one go. But I gave them exercises throughout. So we started out with these functor exercises. So let's not go off and do this on pencil and paper. Let's talk about it together. So suppose we want to make maybe an instance of functor. How do we do that? Well, we need to define fmap. Okay, and when you've got an instance declaration, you don't write down the type signature of fmap, but it's good practice to put a comment there, especially when you're learning, to say what the concrete type, what the types would be. So fmap is defined as f of a and mapping to f of b. Remember, so we plug in maybe here as the functor. So that the signature of fmap is here. So what do you think if we take fmap? If we map f on nothing to the value nothing, what should we get? Nothing, yeah. Okay. And this one's a little more tricky. If we map f over the value just x, what should we get?
Just f of x.
Yeah,
Yeah.
exactly.
Just f of x, right. And let's look at some examples. What do the following produce? So we've got a +1, an increment function there. Increment of just 3, what do you think that should produce?
4.
Yeah, just 4. And increment of nothing. Nothing, yeah. Okay, so really easy stuff. Let's look at applicative functors now. So I'll try and kind of motivate applicative functors to start with. We talked about a functor f mapping a function of a single value to a kind of structure and ending up with a new structure. So we've done f map of increment, just 2 is just 3, for example. But what if we want to map a function of 2 values? So suppose we had an f map primed. We want to define an f map primed. Primed is okay in syntax in Haskell. You know, if you can have primed as part of a variable name, and it's typically used as being a new version of. But let's use it. So we've got the familiar name f map. If we had this function a to b to c, and we want to take an fa, an fb, and map and produce an fc, how can we do that? Okay, we'd end up with f mapped of, take plus, for example, as a that would take a number, another number, and produce a number. If we f map primed f plus over just 2 and just 3, we'd expect to get just 5. So you can imagine writing the implementation of f map primed to get that to work. We won't go into details here and do it. But we've gone from a single value to 2 values here. We've got a new function, f map primed. And so what about 3 values or 4 values? We're going to need a whole series of these things, and it's painful. So the general solution is what's called applicative functors, and they tend to be called applicatives. And it's a bit of an abstract term, but it's actually quite straightforward when you get used to using them. So let's look at the applicative type class. And the concept here is that, again, we've got this kind of lifting function, and it's got a different name for historical reasons, and so it doesn't clash, different from return. It's called pure. So if you take a value a, you can put it into the applicative context using pure. And also just to mention that applicative f only applies when f is a functor. So we're talking about applicative functors here. We're building up a type hierarchy, if you like. And then we've got this other operation, apply, it's called, with a funny star symbol. And this is really interesting. It takes a function, a to b, which is in the applicative context, f a to b, and then it takes an f of a and produces an f of b. So it's like we're lifting f, we're lifting the function a to b into the applicative context and then applying that. Again, f is a type constructor, so f of a and f of b are types, and f of a to b is a type. Yeah, just talked about this. Yeah, so let's look at some examples, start to make that more concrete. So let's look at maybe first. We'll come back to list because that's a bit surprising, but look at maybe. So if we take the function plus and we push that into or lift that into the monadic context, the applicative context rather, sorry, not monadic, applicative, use pure plus, then we're in business. We can start applying that function to a value. And so this associates to the left, and we get pure plus applied to just 2, gives us a function which adds 2 to any given number. So it's kind of like just of plus 2, essentially. Okay, so pure plus will be just plus, and applying that to just 2 would give us pure or just plus 2. And then applying that function to just 3 will give us just 5. So before we go on, is that clear?
I just looked back and compared the type signature for star with the type signature for fmap.
Yes.
It's quite interesting.
Yeah. Yeah. We'll actually come on to that. So if you hold that thought, and we'll look at that and monads as well in one slide. That's when it really starts, the similarities start to become clear. Now for lists, it's really surprising because the definition of the list applicative actually applies the function to every value in the list. So if we take concatenation and push that into the applicative context and then apply that to a list, we apply that function to each value of the list, and that's straightforward. So we're going to get plus plus a, plus plus b, plus plus c, all in a list. Okay, but what happens when we get a list of 3 functions and we apply it to a list of 2 values? Well, the surprise is that the applicative functor definition for a list applies each function to each value in turn. So you end up with ax, ay, bx, by, cx, cy. And it's hard to see an application for this at first, but the classic one is to talk about non-determinism. So if you've got a non-deterministic result, which could be one of 3 things here, for example, A, B, C, another non-deterministic result, which could be X or Y, then concatenating together those non-deterministic results gives you a bigger class of results. Okay, it could be any combination. So that's the way it's normally motivated. And it does have other uses as well, but it's
also very analogous to list comprehension here, isn't it? Sort of what we do with two generators.
Yeah. So we didn't talk about that in the intro because it wasn't needed, but list comprehension is actually syntactic sugar for this.
Oh, that's cool. Okay.
So it's and list comprehension is another good use case where you want to range over particular values and create a list of all the combinations of those values. And there's Haskell syntax for doing that, of course, which you've seen, Adrian. So there are some laws. I'm not going to dwell on these, but they're the same kind of laws before. You can see an associativity coming in here, and some identity operations up there, and some other bits and pieces. A little bit messy, I would say. And just a note, if you go looking at applicative code, you'll see a shorthand. So it turns out that because applicatives are functors, you can write pure f, where f is a function, as f and this dollar operation. And dollar is the infix form of fmap. So essentially, you can do fmap of plus. Fmap of plus is equivalent to pure plus. And that's just a way of doing it. I think to begin with, I prefer the first notation because it's clear that you're in the applicative world using pure and apply. And this is just an abbreviation, really. But it turns out to have the same value. And the first time you come across it, you think, what's going on here? But I just mention it in case you see that. So let's do some exercises on applicatives. See if that's gone in a little bit. So I said that maybe was an applicative, and it is, but suppose we had to define the instance definition for maybe. Then we need to define the behavior of pure and of the apply operation. So let's go through. So what do you think? What do you think pure is going to be equal to? Takes an A and produces a maybe A.
Just?
Yeah, just. I mean, you could write down pure of X equals just of X, and that's the same thing essentially using pattern matching. But yeah, just. So just is a way of injecting a value into the applicative, into the maybe applicative. And then apply has to go through the various cases essentially. So we're using pattern matching here.
Presumably we could have also written pure equals return. Could we? Would that work?
No, because return isn't available for applicatives. Return's part of monads, remember?
Oh yeah, okay. So yes, you're at the wrong level. Yeah,
that's right. We might be able to use fmap, but not for pure. Okay, so let's look at this one now. We're trying to write the star operator, the apply operator, and we're taking a function in a maybe context and applying it to a maybe and getting another maybe. And we just do cases one at a time, essentially using pattern matching. So let's look at this case first. We take a function. There's no function in this case. The maybe context is empty. There's no function, and we apply that to just x. What do you think the answer might be?
Nothing.
Nothing. Yeah, because we can't do anything with the x. We haven't got a function to do anything with. You could conceivably produce just x, I guess, but that would be that'd be the wrong type, because x is of type A and we want a type B. The only way we can get a type B is by applying the function to it, and there isn't a function to apply in this case. Then another kind of failure case, if you like, if we take just f and apply to nothing, what will that give? Nothing. Yeah. Again, we haven't got much option because we haven't got an a value to apply the function to. And then the kind of the case you would like to have most of the time is take a function f, just f, and apply it to just x. What would that give?
F of x.
Yeah, just f of x. Yeah. So, what you'd expect. So again, we're getting that kind of error propagation, if you like, for nothing. But it's two-sided this time. It applies to the function in the context. So if the function is not there, then we kind of get some default behavior, error behavior. And if the function is there and we're applying it to a nothing value, then we get nothing. And otherwise, we carry through. And let's just work that through with some examples. So what does pure plus applied to just 2 give you?
Just +2.
Just +2, yeah. And the brackets, parentheses will be important there, but yeah. And then
is it +2 or 2 plus?
Yeah, +2, I think. I forget the name of that notation, but there's you typically write the binary operator followed by the first value.
Right.
The operator in parentheses, so it's a function applied to the first value. So it's essentially it's plugging the value into the left-hand side of the binary operator.
Okay, so I was right to say brackets 2 plus, close bracket.
Yeah, I don't know whether that's valid syntax.
I think it is. Yeah, you can do it with any two-argued function, and you can supply either the left or the right in those parentheses.
Yeah. Okay. Right. So yeah, that would be a case.
But it's handily associative. So, but in other cases, it might matter.
Yeah. So because plus is commutative, we were okay. But yeah, just 2 plus. That's a good answer. How about this one? So we take nothing and apply it to just 2 and then just 3.
Nothing.
Nothing, yeah. Because it breaks down as soon as we apply nothing to just 2, we end up with nothing. And then nothing applied to just 3 in the same way gives nothing. And then applying pure plus to nothing. What do you think?
Nothing.
Nothing, yeah. So if we applied pure plus to nothing and then to just 3, we'd get nothing again. Because once you hit nothing, all bets are off. And this one's a bit more complicated. It's a slight memory test on what the list applicative gives you. So what does this produce?
3, 4, 6, 8, I think.
Ooh, okay. Any advances on that? Oh, 3, 4, 6, 8. Yes, I heard you correctly now. Yeah, correct. I think it's 2, 4, 6, 8. Yeah, 3, 4, 6, 8. So it takes a function and applies it to each of these values. So we end up with 1 star and 2 star to keep things in the right order. And then applying that to 3, 4, we get each combination. So we get 1 star 3, 1 star 4, 2 star 3, 2 star 4. So 3, 4, 6, 8. Okay, so let's go now from use this to go from functors to monads. we've gone part of the way. We've got functors and applicatives, but how do we get to monads? What's the relationship between the three? Each is a type constructor. They're similar in that way. Each one builds on the previous one. Every applicative is a functor, and every monad is an applicative, and therefore a functor. And this is the thing that Steve was starting to spot earlier. If we look at the operations, so the return and just and return and pure, and the other one, no, return and pure are very similar. But if we start out with fmap in the functor and apply in applicative and bind in the monad, and look at their type signatures, they look a bit similar. There's some T's, A's, some A's maps to B's and stuff going on. It's a bit jumbled, isn't it? But you can sort of see vaguely some similarity there. And I think, Steve, you were talking about this piece here, weren't you? A to B,
Yeah.
T of A to B.
Yeah.
And the rest is the same. So there's some similarity going there. But we can rewrite this. So there's another version of bind, which I don't know how you pronounce it. You can't say it backwards, that's for sure, dnib. But this operation, yeah, dnib. It's the flipped version with the operands in the values in the opposite direction. And if you use that and rewrite these type signatures, then it's easy to compare. So we've got A maps to TB, maps to TA to TB. So look at this. For functors, applicatives, and monads, they're all the same. They're all producing functions of the same shape, which is a mapping from TA to TB. So it's a kind of transformation of TAs to TBs. And the starting point is different in each case. So the type of the input function is the only thing that varies between functors, applicatives, and monads. They're all mapping functions, these input functions, over these functors. And so fmap takes an arbitrary function, A maps to B, okay, completely general, and applies it to the TA, and you get TB. Apply takes an arbitrary function A to B in an applicative context, so TA to B, and it applies that to TA, and you get TB. And then this other dnib maps a class to the arrow, type A maps to TB over a monadic functor. So again, we've got this lopsided thing, A maps to TB, we're applying that. Okay, so that for me crystallizes why you've got this progression, because the signatures are sort of similar. But coming back down to earth, another way of looking at this bind operation is that it's a bit like flat map in some of the languages. I think we've all come across flat map, the people on this call have. So it's a result of applying a class to the arrow and then flattening the result. So take this, for example. If we take the list 1, 2, 3, and we bind that to a lambda expression, a lambda function that takes an x and produces 2 of them, then you end up with 1, 1, 2, 2, 3, 3. You don't get 1, 1 in brackets, 2, 2 in brackets, 3, 3 in brackets, all in brackets, a list of lists. So it's what we talked about earlier, that the bind operation kind of flattens the results and pushes them all together. So as you move from functor to applicative to monad, 2 things happen. You get more expressiveness. You can do much more things, many different kinds of things with monads that you can with functors. Functors are fairly limited. You can do mapping and that's it. But also you get fewer guarantees about the results. So the mapping function in a functor doesn't involve the functor context at all. Okay, so it's not going to affect the context of the result. It maps an A to B. So when you take a list of A's, for example, and you end up with a list of B's, the mapping will never change the length of the list. And that's general for any context. So a functor won't change the context. It just changes the value inside the context. So it's quite kind of restricted in what it does, which is great. It's got lots of guarantees there. It's easy to understand, but you can't do very much with it. You can do that particular operation. In this in applicative case, the mapping function TA to B is extracted from its context. So you can extract the mapping and then apply it. So for example, if you take a non-empty context containing a function, so a list of one function, and apply it to two lists, then the result is always the product of the length of the input lists because of that multiplying effect we saw earlier. And you can't affect that by the function. So it's just predictable. And the same is true for all applicatives, that the apply function, the apply operation, always gives you a kind of predictable shape because you're taking a function and applying it to the existing stuff. But the special case is because the function itself starts out in the context, there can be some special cases. For example, if in the nothing case, there may be applicative. The function doesn't get applied at all because there isn't a function, and you kind of get a default behavior. But when there is a function, it gets extracted out and applied, and the context of the function is kind of ignored. But in the monad case, the mapping function is quite general. So this A to TB creates a context from values. And so mapping over a data structure could produce arbitrary changes. So if you had an A maps to TB that did some sort of editing of a subtree, and you map that over a tree, then you could end up with quite a different shape at the end. You know, all bets are off essentially. So you don't really know in general what a monad is going to do in terms of its behavior. You have to look at the definition. You know the type signature, and you know the concept, and you know the monad laws. But that's all. You've got a great deal of flexibility in about what monads can do. So there are lots of applications of monads. And it's just only limited by people's creativity, really. And the tip, if you're writing Haskell, is to just use as much expressiveness as you need. So if you think you want to use a monad, then be sure you need the monad. If you can get away with a functor or an applicative, that's a lot easier to reason about. Okay, so we're coming into land now. I'm just going to tell you a little bit about the history of how this came to be, because I think this is fascinating. That sequence, functor, applicative, and monad, is the way things are presented now, but that's not the way they arrived in history. Functor and monad first arrived in Haskell 1.3 in 98. And functor and monad were unrelated classes. There wasn't a subtype relationship between them. Functor was briefly a superclass of monad, which is what it is now, in the run-up to 1.3, but that was unpopular and it was dropped. So the community just didn't like that for some reason, because they didn't have the background at that stage. And then applicative came along much later. There's a paper you can find which introduces that in 2008. But again, applicative and monad were unrelated at that point. And some of the dots still needed to be joined. But it turned out that all monads in the standard library were also applicatives because they'd been defined as such. But there was no constraint there to say that a monad was necessarily an applicative. The current definition of the Haskell language, so the standard Haskell, dates back to 2010. They're trying to get a more modern version of Haskell, but it's taken a while to come. And that's got function and monad as unrelated classes and doesn't have applicative at all. so in standard Haskell, you've got functors and monads, you don't have applicatives, and there's no relation between functor and monad. But in terms of implementation, we've got the same thing, that all standard monads are applicative functor instances. And then in 2015, this is where it kind of came together. So it's relatively recently, it's 8 years ago. applicative, and their functor became superclasses of monad in GHC 710. But that structure, that functor applicative monad kind of type hierarchy, is still to find its way into the Haskell standard, even though it's been used in practice and talked about for ages now. And there's some links there. You can download the presentation later if you want the links, and go into some more detail. So, final step is what happens next. What's beyond monads? Yeah, Steve's pulling his hair out. Well, there's some simpler things. You can use monads in various ways. And one fascinating one is software transactional memory. Turns out to be a monad for managing concurrency, if you like. We're not going to talk about that now, but it's just a pointer. If you have various monads like maybe, IO, list, and some of the other ones that you find, parsing monads and so on, how do you combine them together? It's quite fiddly, and you do a lot of things by hand initially, but then monad transformers are introduced as a generic way of combining monads, and there's a nice pattern there that you can apply. There's also an extension of monads called Monad Plus, which has got a notion of choice and failure built in. And then a kind of a really general concept is of an arrow. So we talked about classly arrow. Well, arrow is a kind of more general concept, and it's like it's a generalization of a monad that's not a functor. Now, that it's hard to get your mind around that at this stage, but there's something out there called an arrow, and there are people writing research papers on arrows, and there are people writing parsers using arrows. So it's all there, but it just hasn't really been bedded into the language in a really neat way yet. So it's one of those things that are still in the future, really, as far as Haskell is concerned. It's in the libraries. Okay, so I've got some references there, which you can click on at your leisure. Yeah, some bit of history of functors and applicative functors. Then there's how functors and applicatives fit together. There's a thing called the functional Perl. The functional Perls are kind of articles on functional programming, and this is where applicative came in, applicative programming with effects. That's that paper, I believe. Then there's a little example of my own that shows solving the fox and chicken and grain problem using monads. You can download that and have a look. And it's quite a neat solution with monads, a bit tricky without. And then these slides are at that link if you want to download the slides. So that's the crucial link to make a note of if you want to grab them later. That's it.